Hi guys, so just if you missed the class, there was a demo with what we call the first table. So here I have three loads pulling on those strings. So I have one, two, and three. Here I have 90 grams here. There we have 60 grams. You can see here. And there I have 30 grams. So here I have a small tension. Here I have twice the tension. And here I have 3 times the tension. So here the tension is 3 times as strong than it is here. And here is twice as strong than it is there. Okay. So if you think of vectors, you see there is one vector pulling in this direction, one in that direction, one in that direction. So in equilibrium, you see there is a ring here, and it's not in equilibrium because if I remove the pin, that's gonna fly away, right? So you can move the pulley around until you get the ring here, just such as the pin is at the center and it's in equilibrium. So I'm gonna move the pulley here, and let's make sure we get to okay. What you should see here is that the ring now is at the center. I could remove the pin. I don't know if it's removable. Can remove the pin here, and it doesn't want to move, but if I was about to do it, you see it will be, the ring will stay at the center. So that means that it's in equilibrium. So that force here in if I add that force here for this one plus that one, I should get 0. So if you add the vectors, so it's a vectorial sum, you should get to 0. So when you add those three vectors here, and I will show you how, you should get, they should eat each other out, such as the total sum equals to 0. So I just want to show you that geometrically, and then I will show you that algebraically. So you see here, there is a 0. So you have 90 grams at 0. And it should go counterclockwise here, but there was a mistake when they made that table, because here I should have 90 degrees counterclockwise, and then I have 180 here, and then I should have 270, and here it's going to make 360. So anyway, when it's at equilibrium, I have one tension here, 90 grams at 0 degrees. And here I have 30 grams at, that's going to be, this is 180, so 10, 20, 30. So that's going to be 30 degrees here, going from 180, so going clockwise. So that's going to be at 150 if you use that circle here. So that's going to be 90. So that's going to be 160, what did I say? 160, 170, 10, 20, 30. So 150. So that's going to be 150, 160, 170, 180. So that angle here is 30 degrees. And then here I had 60 degrees at about 180, 190, 195, so 15 degrees. Okay, so that angle here is 15 degrees below the horizontal. That angle here is 30 degrees above the horizontal. So I'm going to make a drawing. That's going to be the demo that we do in class. Okay, so what do we have? Yeah, why not? So I'm gonna have here, so I'm gonna have 30, 60, 90. So you have 90 grams here. That angle is 0 degrees. Then, so this is my x-axis. That's gonna be my y-axis. So here I have 90 degrees. Here I have 180. And here I have 270. So there is a tension here pulling there, and it's just 90 grams. And the angle here is 150 degrees. So that means that angle here is 30 degrees. And then you have another tension here, which is 1, 2. So that's going to be 60 grams. The angle here is about 180, 180, 190, 195. So this angle here should be, it's not on scale, but it should be 15 degrees. Okay, I should have made that more on scale, but I will show you that in a moment, right? But that's the idea. You have 90 grams here, you have 30 and 60, and all the vectors are going to kill each other out. Okay, so just for the math, so you have 3 tension here. So this one's going to pull with 90 grams. Since it's a static equilibrium, so the sum of the forces equals 0. I don't worry about converting to Newton because there is an equality here. So if I multiply everything by a same factor to get Newton, it's not going to change anything, right? So you have 90 grams here. Here it's going to be 30 grams. And here it's going to be 60 grams, right? So now 60 grams, sorry. So 1, 2, that's 30 grams, that's 90 grams. It's not as on scale. If you do it geometrically, so you're gonna add those two vectors, so you can make a parallelogram here. So here I'm gonna make a vector. I'm gonna move this vector here on top of that one. So it's at the parallelogram. Or can tail to head. So the sum here is going to be this vector there. And you see that that vector here has exactly the same magnitude. This is the same magnitude but opposite direction than that one. If I were to do things very well, so I invite you to do it better than not doing it. But if I do it very well, we should get a parallelogram here. So that should be a parallelogram here. And what you get, this vector here will have the same magnitude but opposite direction. So when you're going to add them up, you have 90 here. That's going to be minus 90. They're going to cancel each other out. So that's going to be if you do it geometrically. So you have to use a scale. Which in that case it's not that hard because this is 90, this is 30, and this is 60. So if you do it geometrically, algebraically, so that means the sum of the x component should be equals to 0. It's not a great apparatus, right? It has a lot of room for mistakes, but it's going to work out. So that x component here is going to be 90. Okay. That x component here is going to be minus That's going to be, that angle here is 30. So that's going to be 30 cosine 30 degree. That x component here, so how much that vector is along that horizontal, it's going to be minus 60 cosine 15. And it should about get to 0 because that's going to be about 30 if I round, okay? And if I round, that's going to be about, that's a 60. That's going to be about 60 degrees. About, if you round, so you're going to have 90 minus 90 is going to be 0. Of course, lots of mistakes here because I didn't, there was a lot of friction. There's a lot of friction, but you get the point. Likewise, we should be able to see that the sum of the y component should be equals to 0. So the y component is 0 here. The y component here is about 30 sine 30. The y component here we should be minus 60 sine 15. And if you round everything, you should also get to 0. So it's a very nice demo, except it's not a very good one in terms of lots of friction involved. It should not be there, but it's right for a demonstration.